So I'd like to start the last but not least session of the program. And I'd like to thank Max and Alberto for agreeing to change and be speaking today at this time when everybody is kind of tired. But I'm sure it's going to be lots of fun in both cases. And let me announce also that after the presentation, I'm going to show the full version of Marco Avejaneda's video. So without further delay, it's my pleasure to introduce my longtime collaborator, Professor Max de Souza from the Federal University Fluminense Federal University. Max, please.
So, thank you. So this is the thank you for all for survivor to be in the very last session. Thank you so much. So what I'm going to talk about is, well, nothing really related to Bruno's work, but something that is very dear to many of those people that come regularly to this conference, which is Fourier pricing methods. And this is actually coming back to quite old work. This is Leo Miller was a PhD student that was supervised by me and George at IMPA. And this is kind of going back to an embarrassing long work put on the shelf for an embarrassing long time. So the work's not embarrassing, the work's nice, but just put on the shelf for an embarrassing long time. So just for the sake of the students, and review quickly what are the Fourier ideas in finance, or basic ideas. And then I will spend much more time in talking about the numerical analysis and the computational implementation. So, okay, so as we know, most derivatives really cannot be priced analytically. We like analytical formulas, but they're not easy to come by. And however, even when you cannot solve for the expectation, usually you have the Fourier transform and payoffs are usually available analytically, or in many cases for some Levy process, for instance. But as we know, there is no freelance in finance. You still have to invert it numerically. So not fully analytically, but it's as good as it can be for a more general class of models. And so the idea is to review a bit of the ideas behind, so the aim of the talk is to review a bit of the ideas behind of the Fourier method pricing, and then to tell, to orbit in rigorous bounds, and to discuss an efficient computational implementation. So, so if you write S as XP of xt, with S, or I think X has exponential moments, S has a risk neutral density rho t, then you can just, if you allow me to write this as X plus t, say a contingent claim can then be written in this way, which is really, with this formulation, just become a convolution. Okay, so far as I just have changed variables, nothing really deep here. Now, this is not the standard way people present Fourier transforms. It's a bit different. So what you're going to do is you assume that the risk neutral density is in the Schwartz space of rapid decaying functions, which is in many cases it is. And you see the payoff as an element of the dual that space. So is or to be more precise, is a temporal distribution. So that's is related to the way that Lewis approach this problem, but slightly different in terms of the mathematical formulation. Then if you just do a bit of line calculations, then you can see that the contingent claim pricing is given exactly that. This is an exact formula, no approximation here, and this is just the Fourier convolution theorem. So far, so nothing really fancy. So A lot of strategies and payoffs, they are really combinations of the more vanilla payoffs like calls and sometimes you can include the digitals. So the digital is just a characteristic, step function. The option can be right in terms of step functions as well. And so it's the butterfly or the straddle. So to compute a lot of Fourier transforms of many strategies, all that you need to know to price is combinations of this form. And yes, if you have a general payoff given by this type of combinations of step functions, then you can just plug in the Fourier transform and you have this very general formula, well, at least for this class of payoffs, in terms of the Fourier transformation of your payoffs. Now, this is back to the first papers of Karmadan and even I think probably even Konstantinkov. The problem lies here. So, to invert these two Fourier operators, Fourier operators, is not, or at least to invert numerically precise. That's not easy. And the rest of everything you can do with. Don't have to be to use so clever quadratures to do that, but those bits here are not so standard. So what I'm going to do is spend a bit of the time telling you how do you work on those to approximate those bits here, and doing that, I'm going to do a bit of computational harmonic analysis and extend some previous work on this matter. So let's see how exactly that goes. So the idea is that to have really two Fourier integral operators, which is those two here, and bet is a parameter, typically bet equal the expiration time, and you're going to prove results for this HS in this space class, class of functions, which is essentially they have to be quite smooth and satisfying these bounds of derivatives. Now, H here will come from the kernel, from the spectrum, from the risk neutral measure. And so in the sense you can expect that regularity to be there. So that's not that'll be not really a problem. Usually we see infinity. Of course, I have to check the bounds. So regularity here is not really a problem. So the idea is to extend the results by Greengard and Lane. This is always at that time these results were, when I say this is embarrassing long in the shelf, so they were quite new. And the idea is to try to what they did, they use a spectral approximation of free space heat kernel, which essentially deals on with this type of formula when H is the heat kernel. So the idea is that we're going to try to do to extend Greengard's work in a more general way. So the first thing is that we can, so what's the spectral approximation being used here? You were using the Gauss-Legendre quadrature, which is a orthogonal maximal polynomial quadrature for that for the interval, and this is the error estimate for the exact integral plus the Gauss-Legendre quadrature, provided H is in this space. So this is already an extension of Greengard's work, and essentially gives you a bound on this quadrature, as a more precise bound that what Greengard-Lee was able to get. But the method at this point is really Gauss-Legendre quadrature for that inversion. Now, you want to do two things. Now, you want to treat this integral operator, which essentially has to be dealing with a principal value, and also an operator that present with little decay. So oops, what happened? And there should be an okay. So there should be an something with an IS place C here, which is the other operator that we want to do.
You might want to use the board.
Yeah, that might not too bad. So we want so yes. Notation. So this is say let's say operator 1, and operator 2. Which I'm going to use so yes. So this operator appears when you have some kind of attenuation factor, for instance, naturally. So we can also do some rigorous bound for this case, and you get exactly this well, real looking bounds for the operator, which is for the quadrature rule. I'm sorry, which is well, it's fine. I mean, we have to remember that so for here, I'm not telling the whole story. We are really treating this as a principal value integral. Yes, so I have to be a bit careful of that. But essentially, doing that in a precise way, or a suitable way, we can compute that principal value in terms of those with that precision using the Gauss-Legendre quadrature. So far, so good. And it was there. So this operator appears when you have this attenuation factor. So like Karmadan approach to Fourier transform in this 1990 paper. And then again, we can find a kind of similar bound. So okay, don't have to pay attention. I mean, if you really haven't done these computations before, you're not going to really see too much about what's going to be gained here when this ends and root ends. So instead, let me do a classical example. So let me do the Black-Scholes kernel, which is a bit of anticlimax, really, because we have so long to get to this nice estimates, but turned out to be a good example. So once you choose your kernel, you can go a bit further, and then you can get a really precise estimate for the quadrature for that particular for the particular function that you're using, for the particular Rick distribution that you're using. Now you have now it's been chosen, and so you see that you get more precise. Now, one thing that you have to take in that's something that I'm not calling attention. I mean, besides the n, which is the number of the modes that you're considering, there's also an epsilon, and an epsilon means appears because we're using a non-uniform quadrature. So my integration points are not really I'm not really integrates over the spectral. I mean, exactly on the nodes of the Fourier transformation. And how it compares. So this is the log of error with various examples, and this is the error bound implied by the by Gringard and Lee, and there's the error bound implied by by this equation here. And okay, so of course, I mean, having done that, you really want to do it on a fast way. So basically, we then adapted a non-uniform Fourier transform to this in this context. I mean, this is not that new. I mean, this is at least from Steidel, that 1980 papers has already a formulation of non-uniform fast Fourier transformation, and you can see that if you say compute the Gaussian, the Fourier transform of the Gaussian, you can see that the Fourier transform, the non-uniform Fourier transform is much better in terms of error approximation, even if it's oscillating here. But it's particularly true if t is large. So we have lost quite a lot of the precision here, but that is particularly spectacular because we have the freedom to adapt to the both regimes of the payoff. And if you then compute it again for so take 8, the density given by black shows, and you can compute 8s. That's exactly what we're doing. The solid line is the difference between the spectral code against what is that? Gauss-Conrad scheme. Now, Gauss-Conrad scheme is to take Gauss-Legendre scheme, add a bit of points, and so you get a quadrature that is order 2n plus 1 rather than the order 2n minus 1. So you get a bit more of conversion of order, and you see that the bound behaves quite nicely. I mean, except that here you start to see some numerical rounding errors. You still have good enough bounding. A bound if you have computed the hs over s. And I think this is also true for the case of the CS, IS plus some constant. Now, in this case, was chosen to be 1. So if those bounds shows that, I mean, what it works and gives an example that how nice the code, the quadrature rule can integrate, and how good actually the numerical bounds work to predict your the numerical error. And of course, I mean, having gone this way, you can compute the price of a call, which is not so exciting, but with a very, very precise error with not so many modes. Yes, and I mean, if you look at Madan's paper, he would ask you to use, I think, 248 nodes, 2048 nodes. I think that's what's modes. Sorry, I think that's what's here, or 40,096. I don't remember now. I think it was 40,096. No modes, and so you only use those bit of smallest nodes actually do the work here. And so that was short because well, that was a short talk anyway. So for here, short talk, going to compress a talk. So the idea is that we have this numerical bounds for a class of Fourier integral operators that can be efficiently implemented for European options. At some point, we would have all these plans. I think that the current plan is to rescue what is there and try to write something because it has been long enough in the shelf. And I think with that, thanks a lot for your attention.
Okay, thank you very much, Max. So, in the good tradition of panel talks, we are going to have the talk now by Alberto Pinto.